what we have now, after we've graphed sine and cosine, this is the parent functions. All right. So what we want to do is we want to manipulate these. We want to get them to, increase their height or kind of squish them together like springs, either towards, crest to crest closer or crest to crest farther. Okay. We can kind of spread them out. See, light behaves as a wave and a particle as well. So, or I think they call it a particle wave. So light, for example, if it is stretched out, it is actually more, it goes towards the blue end of spectrum until ultraviolet light, where you can't see it anymore. As light waves squish together, closer together, okay, where their cycles get closer and closer, quicker and quicker. That means you see more red, okay? The color spectrum goes closer to red. Eventually into infrared, where we can't see, to microwaves, and so on and so forth. So waves are incredibly important in physics. So what we're going to do in this last video for tonight is we're going to do enough where you can kind of tackle your homework over the next couple days. And we have these parameters here. We have an A, B, a C, and a D, just like we would like quadratics or polynomials. You put a number in there, and what change does it have? Like, what effect does it have on the actual function? And we're going to focus on this one right tonight. It's the A, and it's actually the amplitude. Okay. Now, the amplitude is basically the distance from the axis of symmetry to the max or the min point. So the axis of symmetry is actually, it's the middle. Okay. The axis of symmetry is the exact middle where the average is pretty much displayed. Like right here, sine, the average is actually at 0. Okay. So the axis of symmetry is 0. And so this distance from here to here is actually the amplitude. And that's true for cosine as well. And you can see that they have identical amplitudes. They both have a height of 1. But also the amplitude has to be calculated downward as well. So the amplitude is still 1, but it's 1 up and 1 down. Okay, so we say that the amplitude is 1. The amplitude is not 2. Okay, that would be called peak to peak. Peak to peak, it's 2, but that's like an electrical term. Okay. So peak to peak would be 2, but its amplitude is just 1, and it's not -1 either. It's just 1, okay? All right. So what we're going to do is we're going to look at this guy here, -3 sine x, all right? Now, your homework is only going to have just changes in the amplitude. Now, try to think of what a negative sign in the front means, what it has always meant with all of the other I did not push record. Did I push? I did record. Oh. I thought for a second I didn't push record. All right. So, what has, no, I forgot what I was going to say. Okay. So a multiplier, what has a multiplier always done to a function? Well, if it was a quadratic, it made it more steep. If we put a negative sign in front, what did it always do? It just flipped downwards. Okay. So let's look at Desmos here. So let's say that I got y equals x. Okay, here's our sine curve here. Now what I want to do is I'm going to go ahead and go to this first and change it. I'll put an a in front of it. I actually want a slider here. Now you can see when a is 1, has an amplitude of 1. All right, you can hear. Okay, right there. Okay, so you have an amplitude of 1. All right, now let's actually increase it. Okay, so notice. I'll give you a couple seconds to think about this. As I go more and positive, and if this one way, what's happening to it, that the volume is increasing. It's getting louder. Okay, the pitch is not changing, it's getting louder. For example, what is what? So notice is that with a y equals 2 sine x, which is what we have here, a equals 2, you'll notice that the amplitude went too high here and it went too down here. But notice that these zeros stayed the same. It's basically an anchor, okay? So the 0, if just stays planted, it's a root, okay? That's kind of why we call them roots, okay? All right, so they anchored where they normally would be 0, okay? Once I get into negative, that's sine wave has actually reversed direction. Okay, so now instead of up here and coming back down, it actually down first. So it completely flipped the x-axis. Okay, let's go back to 1. This is here. Okay, we have an amplitude. So what I want you to do is that this is in radians, and so if you were to look at where sine actually hits 0 at pi, and it hits 0 at 2 pi, okay? It hits 0 at, well, it hits 0 at 0, 0 at pi, and 0 again at 2 pi. Here, notice that it's 0. And right here, that value right there is actually pi. You can see in parentheses pi 0. Now that's actually 3.141592654. So that's off. It's not 3. 3 is good enough for an engineer building stuff, okay? If you want to be really exact, you want 0.4. So there it is right there. And if you go here, that's at 2 pi, and that's 6.28, et cetera, et cetera. So it's basically pi doubled, okay? So these are in radians, and that's why it's not going to land on a perfect number here. It's just not. These are all the values along the circle going around. All right, so finally, when we're going to go back to our notes here, we're actually going to do -3 sine x. So what I'm going to do for almost every single one of these in the beginning is I'm going to go from -pi/2. All right, so I'll always go just a little bit to the left of the origin. I will go all the way to 2 pi. I will cut him in half for a pi. Okay, so that would be the full circle. I will go as high as my max will allow me and as low as my max will allow me. I will also cut pi in half, and I will put 3 pi/2. So that's basically the 4 kind of corner points around my unit circle. So if I'm going to graph sine would normally, you know, he would just kind of go up to 1, come back down to 0, go down to -1, come back up, just like what we graphed here. But with a -3, that changes it. What's now happened is that the amplitude is actually going to go as high as 3 and as low as -3. All right, that's going to be its amplitude. That's as high as it will go. But because it's negative, all right, that means then that I'm going to be going not upwards first. Okay, this sine wave wants me to go positive first, but I'm actually going to be going this direction. Okay, so this whole thing will basically rotate along the x-axis. Now, what I'm going to do, though, is when I put my zeros, these are my anchor points. They will stay anchored there at 0, pi, and 2 pi. I'm not shifting to the left or right. I'm not moving up or down. I'm just basically pulling on the 2 peaks, okay? And I'm keeping them, the anchor points, still anchored. Okay, so this means that with that, I know that I have to go as low as -3, as high as +3, and then coming back down. Now, what I want to do, and what I'm expecting in your homework, is to make sure that you put arrows to show that this actually does keep going. Okay, now this one's a little crooked. I should have made it more of a curve there, but you kind of get the idea. This is good enough for paper. Okay, all right. So just to kind of clarify, this right here, this axis of symmetry, okay, is also called the node. Is it the node? The node or the mode? I forgot. Let's call it the node/mode because I forgot. I think it's the node. I think it's the node. All right. And it just means the average. Okay. It's kind of like the 0 point. All right. So we'll put that, and I'll Google that, or you can Google it right now. It's either I'm pretty sure it's the node. But the axis is basically where things can reflect on. Okay. It's normally the x-axis. Now, this thing was not vertically translated or horizontally translated. And that, of course, is where this and this come in. But tomorrow, we're going to go over what that B does, okay, and how it changes the accordion effect that squeezes in or pulls it outwards. All right, so that should be enough to actually do your homework. I will actually, if I can remember tomorrow, I'll do like a couple examples, like 1 or 2, and that way you can kind of see how you're doing, and then we'll go from there. All right, so more videos tomorrow. Have a good